Good morning. I just wanted to give you a heads up on the way things are going to look from here on out. First of all, at the beginning of the week, you'll have one or two video lectures from yours truly, and you'll watch those videos. You'll get 10 points for that. Then throughout the week, you will have a short problems assignment, 5 problems, typically 3 points each. That's going to be a 15-point assignment. Add those together each week, you'll earn 25 points. And you're going to do 2 weeks of work at a time. So you'll turn it in all at the end of the 2 weeks for a total of 50 points. And that's going to be how it's going to look. So for right now, I'm going to go into kind of a little bit of a longer lecture. So what you've been reading about in the textbook was all about the properties and behaviors of gases, right? You went into gas laws, etc. In order for gas laws to make sense, we need to review a little bit about the types of matter and talk a lot about the properties of gases in general. So I'm going to bring up our PowerPoint. Now, usually you would take notes over this. That's not such a deal breaker for me now. If you choose to take notes, you can pause the video at any time and write down the notes on that slide. It certainly would not be harmful to you to have these notes. However, there won't be a test over it. It would be useful material to carry on to AP in the future or to college. So I'm going to let you row your own boat on whether or not you take notes. If you want to, awesome. If you don't get a chance, that's okay too. Simply by watching this video, you are getting 10 points. So that's awesome, right? So I'm going to flip over so that you can see my PowerPoint. Okie dokie. All right. So we're going to quickly review solid, liquids, gases with going into detail on gases, okay? Of course, you know that skunks release that distinct odor. We're not going to go into that too much. So we need to talk about kinetic theory. So you know that kinetic means motion, and kinetic energy is energy that something has because of its movement, okay? So kinetic theory of gases is all about the movement of the tiny particles that are contained in a gas, okay? So here are some assumptions that you make with kinetic theory. Particles are in a gas state and they're small hard spheres with insignificant volume. Insignificant means essentially can be rounded to 0 volume. So super, super, super tiny particles. They are in constant, rapid, random motion. Those tiny particles are zigzagging all over the place, never ever stopping and never going in a pattern. Collisions between those particles are completely elastic. What that means is if you've ever watched a DVD screensaver and it bounced all over the screen, but it never slowed down, that would be an elastic collision. No energy ever lost, no matter how many times you hit the side of the container or another particle. So according to kinetic molecular theory, gases are in rapid random motion. They travel in straight line paths. Again, just like that DVD player screensaver, whoop, 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 hitting all the sides, but never ever stopping. Gases also fill the size of the container. How does kinetic theory explain gas pressure? Well, first of all, gas pressure is a result of the particles hitting the side of the container. So, for example, the reason why a tire stays inflated is because the gases within the tire are constantly hitting the rubber on the outside of the tire. If that were not to happen, if there were no particles present, we would call that space a vacuum. And in a vacuum, there is no pressure at all present. Now, this is not like a Dyson vacuum, okay? Those are two different concepts. This vacuum means that there are no particles at all present and therefore no pressure. Atmospheric pressure is what we are always experiencing from collisions with the air around you. So you're constantly experiencing atmospheric pressure. That does change depending on elevation. So in Colorado, they are experiencing less atmospheric pressure than we would here, simply because they have a higher elevation and therefore less atmosphere pushing on them. So gas pressure is the result of collisions of literally billions, probably more than that, atoms rapidly moving and making contact with any object. So the atmospheric pressure that you feel is essentially the particles of the atmosphere, oxygen, nitrogen, carbon dioxide, all those things pinging off of your surface. You don't realize that you're experiencing that because you always experience it. A barometer measures atmospheric pressure. And it essentially, here's kind of like the basic diagram of one, a dish of mercury with a tube. The more that the atmosphere pushes on the mercury, the more the mercury is forced into the tube. The less pressure on the mercury, the less the mercury fills the tube. So atmospheric pressure is usually measured in millimeters of mercury, because it's quite literally how many millimeters the mercury moves up the tube. That is interchangeable with torr. So torr and millimeters of mercury are interchangeable units. They have they take up the same amount of space. The standard unit of pressure is the Pascal. However, pascals are quite tiny, so we often use kilopascals, which is kPa. And then one standard atmosphere, ATM, is another unit of pressure. So these can be interchangeable. 1 atmosphere equals 760 millimeters of mercury equals 101.3 kPa. Now, I know I said you didn't have to write any notes, but if I were the note-taking kind, this is an expression I would certainly have written down. Because sometimes in problems, you will be given millimeters of mercury for pressures of one thing, but maybe kilopascals for pressure of another, and they have to be apples to apples, so you may need to convert. And the relationships here are what we use to convert. Of course, we will practice that. All right, so speaking of converting between units of pressure, a pressure gauge records a pressure of 450 kPa, kilopascals. What is this measurement expressed in atmospheres and millimeters of mercury? So if I'm trying to go from kPa to atmospheres, I look at how many atmospheres equals how many kPa, and it's 101.3 to 1. So that's the conversion factor I would multiply by 450 by. And then to get to millimeters of mercury, I would say, okay, 101.3 kPa equals 760 millimeters of mercury. This is the ratio I would multiply by. It would be set up like this. kPa would cancel here and you would get atmospheres. kPa would cancel here and you would get millimeters of mercury. For sig figs, well, honestly, these are both 2 sig figs, so it's really not concerning. But if you wanted to put it in scientific notation, you could do so. Okay. All right, I'm going to go on. So kinetic energy and temperature. So they want to know, what is the relationship between kelvins, which is a unit of temperature, and average kinetic energy of particles? So first of all, for gas laws, temperature always needs to be in Kelvin. If it's not, you need to convert it to Kelvin, and we'll talk more about how to do that later. Because, well, I don't want to get ahead of myself. We'll talk more about Kelvin in just a second. Kelvin temperature is directly proportionate to the average kinetic energy of the particles. So I want you to think about this. You know, if you go back to the first slide and you look at the picture of a solid, a liquid, and a gas, they're all made up of tiny particles that are constantly moving just a little bit. Okay, and the higher the temperature goes, the more those particles are moving. Okay, higher the temperature goes, the more likely it is to be a gas. You know that. So, at the gas state, lower temperature gases are going to move kind of slowly, and then high temperature gases will move super, super fast, like the way Miss Beavers talks. Okay, so the relationship between the temperature and the movement of those particles is direct. And since kinetic energy is the measurement, the energy associated with movement, the faster I move, the more energy I have. So here's a diagram of cold water versus warm water. So speaking of Kelvin and why it's important, absolute zero is 0 degrees Kelvin. It's the theoretical temperature at which all motion stops, all particle motion stops. A particle at 0 K would have 0 kinetic energy. This has never been done in real life, okay? We've gotten to fractions of a Kelvin, I think 0.2 or 0.4 or something like that Kelvin. We've never gotten all the way to absolute zero. There's a fantastic video. If you haven't watched it in my class, you should go out and watch it because it's awesome. It's a Nova Science video, and it's called Making Stuff Colder. And they talk about basically going from room temperature all the way down to fractions of a Kelvin and the weird stuff that happens at super, super low temperatures. Okay, this is a vacuum chamber that is cooling sodium vapor to almost absolute zero, not quite. You can do these section quizzes on your own. I'm going to flip through so that I'm not taking up too much of y'all's time. Oops, let me go back real quick. Oh no, we're good. Okay, so we're going to touch on liquids really quickly. Two factors that determine the properties of a liquid: the interplay between the disruptive motions of the particles of a liquid and the attractions determine their physical properties. So we're not going to talk too much about liquids, just kind of to be able to contrast liquids and gases. Liquids and gases are both fluids. Usually when we use the word fluid, we are thinking of a liquid. However, gases also are fluids. A fluid is anything that is pourable, and you can see that this dense gas is pourable just like a liquid would be. Okay, properties of liquids. Their particles are close together, not as close as solids, but closer together than gases. They are somewhat attracted to each other. So again, intermediate attraction there, not as attracted as a solid, not attracted as a gas. They flow and they slide around against each other, the particles do. In order to escape and become a gas, they have to break their intermolecular forces, which requires energy, which is why you have to heat up water in order to boil it, because water really likes water. Okay, so it's going to take energy in order to break those molecules apart and allow them to become a gas. Speaking of that process, how does evaporation work? So during evaporation, only a few of the particles within the sample have enough kinetic energy to leave the liquid state. So, and you know this, evaporation happens slowly and not all of the water does it at the same time. Anytime something goes from a liquid to a vapor or a liquid to a gas, remember the difference between liquid and vapor, but we'll get back to that, is called vaporization. That's the general term. Evaporation is a special kind of vaporization. Evaporation happens below a liquid's boiling point. It happens at a lower temperature. Okay, I want to go back to that because I just want to add something. Boiling, okay, is different than evaporation because it's when all of the particles within the liquid sample have enough kinetic energy to leave the liquid state. Okay, so boiling happens at a substance's boiling point. Evaporation happens below a substance's boiling point, but both boiling and evaporation are subsets of vaporization. Okay, vapor pressure, dynamic equilibrium that exists between a liquid and its vapor. So first of all, dynamic, ever changing. Equilibrium means the forward and the reverse are occurring at the same time. So kind of how does the relationship between a gas and a liquid constantly change? Okay, so a system at constant vapor pressure, a dynamic equilibrium exists between the vapor and the liquid. So essentially, if it is a closed container, the evaporation and the condensation are going to occur simultaneously. And this is a great expression of that. So if the vapor pressure is constant, evaporation and condensation will equal. We change that vapor pressure, it pushes it one direction or the other. Okay, I'm going to flip through this pretty quickly because these aren't the main points that I want you to see. This is just kind of background info. Okay, so boiling, when does it happen? Boiling is when a substance is heated to a temperature throughout the whole entire sample that all the particles have enough energy to vaporize, not just the surface like evaporation. The temperature at which, let's read this together. The temperature at which the vapor pressure of the liquid is just equal to the external pressure on the liquid is called the boiling point. So when the outer pressure and the inner pressure are just equal, we call that the boiling point. Of course, you know, liquids don't boil at the same temperature. Different substances have unique boiling points, but also pressure affects that. So, for example, as we talked about earlier, Colorado has a higher elevation than we do here. And so in Colorado, you have less pushing on the surface of your substance. So that water will boil at a lower temperature. It'll boil faster than water will boil here. Okay, so here's exactly what I was just saying. At sea level and then at Mount Everest, water boils at very, very different temperatures and because of a difference in pressure. So you can see here at regular altitude, 101.3 kPa is what our atmospheric pressure is. At 70 degrees, water is not boiling, 70 degrees Celsius. But at 101.3 kPa and 100 degrees Celsius, our water boils. Well, on top of Mount Everest, you only got 34 kPa, which is about a third of regular atmospheric pressure. Water boils a lot sooner, 70 degrees Celsius, which is still pretty warm. And I mean, that's, you got to think Celsius have bigger degrees than Fahrenheit. Here are just some vapor pressures and boiling points of different substances. It can be helpful to determine a substance's identity using these type of curves. A normal boiling point is the boiling point of a substance at standard pressure. Here's some boiling points. The only one you have to know is water is 100 degrees Celsius. Not going to go through this section quiz. Not going to go through using atmospheric pressure. I really would like to. This is something that I really like to do as a lab, is a can crushing lab. I would not want to crush a railroad car. No, definitely not. But I have done the can crushing. And a couple of years ago, Mr. O'Connell and I did a barrel crushing where we heated up a barrel and then inverted it into water and crushed some 55-gallon drums, which was pretty cool. Wish we could do that. So solids. How do solids work? I'm actually going to entirely skip solids for right now. I hate to, but I don't want to make this lecture super, super long and then you just totally tune me out. We're really worried about gases right now, so I'm just going to skip through solids. Sublimation is when something skips the liquid phase and goes straight from solid to gas. Dry ice is your prime example of sublimation, and we use dry ice during our Halloween demos, okay? So it starts off as a solid and goes straight to the gas phase. This process is called sublimation. Mothballs do that too. Okay, phase diagrams. On a phase diagram, it would be better if I just showed you. So you can see you have temperature on one axis and pressure on the other. And the phase diagram shows at what temperatures and pressure something is a particular state of matter. So for example, this is the phase diagram of water. At between 101.3 kPa and 0 kPa, or a little over 0 kPa, up to 0.016 degrees Celsius, it's going to be a solid. So anywhere in here, it's going to be a solid. But let's say I drop that pressure and increase the temperature, it's going to be a liquid. And then, let's say I keep pressure constant, but I increase temperature, I go from solid to liquid to vapor. That makes sense to us. We know we could take an ice cube at the same pressure and heat it up, and it's going to become a liquid. Take the same ice cube, continue to heat it up, and it's going to become a gas. So this just demonstrates that. The triple point, which is this little dot right here, is the set of conditions where all three states of matter exist at once. This is a picture of this being done in a lab. This tube is holding the pressure constant by piping in gas if needed, or suctioning off gas if needed to hold it at a particular pressure. So you can see the ice chunks in there along with some water, and there is steam. It's kind of hard to see the steam, but all three states of matter of water are existing together there. Okay, properties of gases. This is the part I really want to dig into. So you know, you could take a block of wood and you could push on it, and it's not going to change in size. Not really, not unless you push on it with, I don't know, an anvil, a hammer. But you push on that block of wood with your hands, it's not going to change in size at all. But you do the same thing with a balloon, and it does change in size, okay? So gases are more easily compressed than other states of matter because there's so much space between their particles, okay? A gas is actually composed of mostly empty space. When you push them under pressure, their particles are forced closer together and therefore occupy less volume. Compressibility is a measure of how much a particular sample can be decreased in volume. So at room temperature, the distance between particles of an enclosed gas is about 10 times the diameter of a particle. So think about that. About a tenth of a 1/10 of a gas is actually made of particles. The rest is space between those particles. All right. The amount of gas, volume, and temperature all affect the pressure of a gas. These variables all affect each other, okay? So we need to talk about pressure, which is symbolized by P, usually in kilopascals. Volume is usually in liters. Temperature is usually needs to be in Kelvin for our calculation. And then number of moles is symbolized by N, and it will just be in moles. Oftentimes, you can leave these in the units that they occur in as long as they are both that same unit. So you usually have two pressures in a problem. As long as both are in kilopascals, it's fine. You don't have to convert it. But if one is in if one is in millimeters of mercury and the other is in kilopascals, you have to convert them to be the same. Same thing is true with liters. Generally, if it's in milliliters, as long as both are in milliliters, that's fine. But it never hurts to convert it to liters just to be safe. But temperature always has to be in Kelvin. Okay, I'm going to go through amount of gas pretty quickly. I'm going to go back to it real quick. If I have a few particles, I exert a little bit of pressure. If I have more particles, I exert more pressure. And that continues. So you know that. I'm not going to go through that too much. All right, volume, amount of space something takes up, right? So if I increase pressure, I decrease volume. Temperature also affects pressure. The faster those particles are moving, the more pressure they're going to exert. They're going to hit the container harder. So at a low temperature or a moderate temperature, my particles are moving moderately. As I increase temperature, those particles are moving faster and hit the container harder and exert more pressure until the container explodes. Okay, I'm almost to the last part, gas laws. This was what your textbook hit the most on. And these are relationships between pressure, volume, temperature, number of moles. Okay, the first one and the only one we're going to talk about this week is Charles' law. And I'm not positive there should be two S's on that, but okay, Charles's law. I feel like there should just be an apostrophe. Temperature and volume. They have a direct relationship as long as pressure is constant. So for Charles' law, pressure is constant in all of these problems, okay? So if you look at, this is a balloon that is submerged in a beaker, okay? And then there's another beaker holding on top of it, so the balloon stays into the water, okay? You can see at a higher temperature, 373 Kelvin, the balloon expands. But if you drop the temperature to 365 Kelvin, more than 100 degrees decrease, you can see that the balloon shrinks, right? It's occupying most of the beaker on the right, but on the left, it's about, I don't know, half of the beaker. So as temperature decreases, the volume of that balloon decreases. As temperature increases, the volume of the balloon increases. So the relationship looks like this. V1 over T1 equals V2 over T2. I'm going to grab my stylus because there's something I want to change here. This is the mathematical expression and the relationship between volume and temperature. I usually rewrite it as, I need to use my stylus. I guess I need to pick. Okay, here we go. As V1 T2 equals V2 T1. You can see what I've done. I've just kind of cross multiplied these to have an expression without a fraction in it. And that is the expression that I prefer and the one that I'll be showing you problems using. Okay, so you can see Charles' law, volume and temperature directly related. Temperature does have to be in Kelvin, and let's talk about why. I didn't talk about that earlier, so I'm going to hit on that now. Celsius goes negative. That messes up this relationship, right? So we want these to stay, the temperatures to stay positive. Charles's law is built on only positive values for temperature. So we have to use Kelvin. As temperature increases, volume increases. As temperature decreases, volume decreases. Let's work a problem. A balloon is inflated at 24 degrees Celsius. That's your initial temperature, or your T1, and has a volume of 4 liters. So that's your volume 1. The balloon is then heated to a temperature of 58 degrees Celsius. That's your T2. What is the new volume if the pressure remains constant? That pressure remains constant part is essential. If pressure doesn't remain constant, it's a different law. We're not worried about it this week. So we need to remind ourselves what our expression is. V1 T2 equals V2 T1, right? What do I have? What do I not have? I have volume 1. I have temperature 1. I have temperature 2. So what do I not have? I don't have volume 2. That's what I'm solving for. That's my question mark. So how can I rearrange this equation to get V2 by itself? I could just divide both sides by T1, right? So V1 T2 divided by T1 equals V2. Again, we'll practice this more. Then I just plug in the values from the problem. Hold on, Miss Beavers. This is in Celsius. This is in Celsius, isn't it? That cannot remain in Celsius. Remember we said that we have to convert to Kelvin. Well, how do I convert from to and from Kelvin? I didn't tell you that yet, did I? So you take Celsius and you add 273 because 0 degrees Kelvin is 200, reverse that, 0 degrees Celsius, 273 degrees Kelvin. So to find T1 is equal to 24 plus 273. Okay, 24 plus 273 is 297. Okay. T2, 58 plus 273. 331. Okay. Now we can just plug it in. Okay. So volume 1, 4.00 liters. T2, we decided was 331 Kelvin over T1, which we decided was 297 Kelvin. Okay, so what I want you to see is since Kelvin repeats on top and on bottom of this fraction, it cancels. What are we left with? Liters. Okay, so I do 4.00 liters times 331 divided by 297. 4 times 331 divided by 297. Okay, now I have to consider significant figures here. All of these values, I lied, look, okay. Yeah, all these values have 3. So this one has 3, that one has 3, and that one has 3. I will talk about some more about that in just a second. So you end up with 4.457. So we're going to round that to 4.46 liters. Okay. I know what you're thinking, you guys, on sig figs, that 24 degrees Celsius has 2 and that 58 degrees Celsius has 2. But remember, when you add, like we did over here, you keep the place value. So that was all good. We did that correctly. And then once you do that, you actually added a significant figure. So you can keep that, all 3 of those there. Okay, so they've worked this out for us. So let's take a look at that too. I mean, hey, why not? And look, they came up with the same answer. I just did it for you. I didn't realize it was all done here. So you take the temperatures, convert them to Kelvin, and then you do V1 T2 over T1, just like what we did here, 4.46 liters. Okay, need to evaluate and see if this makes sense. So go back to your initial problem. You started at a low temperature, you went to a higher temperature. What's the relationship between temperature and volume? They have a direct relationship. So as temperature increases, volume should also. Did my volume increase? Yes, it did. Good job, you guys. So that made sense. Okay, we're gonna stop here. You guys have been a great audience. I really appreciate you being patient with me throughout this process. I know it's gonna take some getting used to, I'm trying to figure out how to turn off my screen share. Okay. So it's going to take some getting used to figure out this whole online learning thing, but I really appreciate your patience. I hope you guys have an awesome day. Make a choice.